Welcome back to The Lost Tactician. Now picture a waterlogged trench stretching endlessly through Flanders mud, reinforced with timber that honestly should have rotted within months, but somehow held firm through years of shellfire and flooding. Imagine, if you will, railway ties supporting supply lines across scorched deserts and frozen tundras, their wood somehow resisting insects' decay and the relentless crush of locomotives carrying the machinery of war. Today, we're going beyond the battlefield to uncover something extraordinary, how the desperate crucible of conflict transformed our understanding of wood itself, forcing material scientists and field engineers to unlock secrets of timber longevity that peacetime research never imagined. This isn't just about preventing rot, this is about the forgotten revolution that made wood nearly immortal. It sounds impossible, but the harshest battlefields actually birthed some of the most ingenious ways to make wood last forever. We're about to expose the shocking truth wartime exigencies, not peaceful research, unlocked secrets to timber durability that are still relevant today. So, prepare to see wood in a whole new light. The desperate call, why wartime timber was different. The scale of timber consumption during the World Wars, well, it truly defied comprehension. Millions of tons disappeared into the construction of barracks stretching across continents, bridges spanning bomb-cratered rivers, and ships whose wooden decks faced saltwater corrosion while dodging torpedo strikes. Underground command bunkers required timber supports that could withstand not just time, but the concussive force of aerial bombardment. Trench systems consumed forests, their support beams subjected to perpetual moisture, freezing temperatures, and the unique chemistry of gas-contaminated soil that accelerated decomposition beyond anything seen in civilian applications. Pre-war preservation methods seemed, honestly, a bit quaint against these demands. Traditional techniques like surface charring or simple tar applications might extend wood's life by a few years under normal conditions, but the battlefield presented conditions that were anything but normal. A dock piling in peacetime might gradually succumb to marine borers over decades. In wartime, that same structure needed to survive not only biological threats, but also the chemical contamination of fuel spills, the mechanical stress of rapid construction and demolition, and the ever-present threat that replacement might be impossible when supply lines collapsed. The engineering challenge wasn't merely preventing rot, it was creating timber that could endure apocalyptic conditions while maintaining structural integrity under life-or-death loads. When a bridge's failure meant stranded troops and a lost offensive, when rotting ship timbers could sink an entire convoy, the old methods weren't just inadequate, they were lethal. Chemical warfare on wood, these were truly the early breakthroughs. The revolution, began with chemistry as aggressive as the warfare surrounding it. Scientists and engineers discovered that heavy metal salts, particularly those combinations incorporating copper and arsenic, didn't just poison the microorganisms that caused decay. They fundamentally altered wood's interaction with its environment, creating barriers against insect invasion and, reinforcing cellular structures to maintain strength even under extreme mechanical stress. Creosote, which is this thick tar derivative from coal processing, became warfare's preservative of choice because it offered multiple layers of protection simultaneously: fungicidal, insecticidal, and water-repellent properties that turned vulnerable timber into something approaching permanence. But application was everything. Surface treatments, honestly, failed spectacularly under combat conditions where water intrusion or physical damage would expose untreated core wood within months. The answer, as it turned out, emerged in pressure treatment facilities that transformed preservation from an art into an industrial science. The full cell process represented a breakthrough in material engineering, technicians would place massive timber loads into cylindrical vessels, apply vacuum pressure to evacuate air from the wood's cellular structure, and then force preservatives deep into those evacuated spaces under pressures exceeding 100 pounds per square inch. The result was timber, impregnated not just at the surface but throughout its entire cross-section, with preservative chemicals bonded into the cell walls themselves. Railway sleepers became the proving ground for these techniques. As supply trains formed the literal backbone of military logistics, the ties supporting those rails faced punishment that would destroy untreated wood in a single season. The crushing weight of armoured trains, the chemical assault from coal ash and locomotive oils, and exposure to every climate from tropical monsoons to Arctic permafrost. Pressure-treated sleepers lasted decades instead of years. Dock pilings, meanwhile, transformed from expendable components requiring constant replacement into permanent infrastructure, their treated wood resisting the dual threats of marine borers in saltwater and bacterial decay in oxygen-starved mud. Even aircraft components, where weight considerations normally precluded heavy chemical treatments, received experimental preservative applications that extended service life in the harsh environments of coastal patrol bases and jungle airstrips. The truly revolutionary innovations emerged from necessity's most extreme demands. Field engineers facing immediate threats developed flame-retardant treatments for timber in defensive positions, recognizing that wood's flammability represented a critical vulnerability when incendiary weapons could transform fortifications into crematoriums. Chemical compounds incorporating borax and other fire-suppressing agents were painted, sprayed, or pressure applied to reduce ignition temperatures and slow flame spread, buying precious minutes for evacuation or firefighting when artillery created conflagrations. Anti-splintering treatments addressed a threat unique to modern warfare: the horrific injuries caused when explosive shells struck wooden structures. Traditional timber would shatter into thousands of razor-sharp projectiles, each splinter a potential wound that festered and killed. Researchers developed penetrating resins that increased wood's flexibility while maintaining strength, allowing it to bend and crack rather than explode into lethal fragments. This same principle protected vehicle crews where wooden components remain necessary for weight or insulation reasons. The most forward-thinking innovations pushed into territory that wouldn't fully develop until decades later. Synthetic resins, crude ancestors of modern polymer treatments, were experimentally applied to encapsulate wood fibers or even replace portions of degraded timber with plastic infusions. The Forest Products Laboratory and military research facilities explored chemical modification at the molecular level, treatments that altered wood's fundamental chemistry to make it less appealing to biological attackers or more resistant to moisture absorption. Field engineers, meanwhile, displayed remarkable ingenuity. With whatever material circumstances provided, used motor oil mixed with diesel fuel for emergency preservation, copper sulfate solutions scavenged from agricultural supplies, even experimental applications of saltwater brines in coastal areas where traditional preservatives were unavailable. These improvised treatments rarely matched laboratory standards, but they kept critical structures standing when replacement was impossible. When peace finally arrived, the military's preservation breakthroughs didn't remain buried in classified reports. The techniques proven under fire became the foundation of modern timber treatment standards. Chromated copper arsenate, refined during wartime urgency, dominated residential and commercial wood preservation for decades. The compound's genius lay in its fixation. Chemistry chromium didn't just preserve the wood, it chemically locked copper and arsenic compounds into the cellular structure, creating treatments that resisted weathering and leaching far beyond anything previously achieved. A CCA-treated utility pole could stand for 50 years or more, supporting power lines through hurricanes, ice storms, and the relentless assault of insects and fungi. The pressure treatment processes developed for military applications became industry standards, with treatment facilities around the world using equipment and protocols directly descended from wartime innovations. Yet this legacy carried complications. The same heavy metals that made CCA so effective raised environmental and health concerns as scientists better understood bioaccumulation and ecological persistence. Arsenic leaching from treated wood into soil, copper contamination in aquatic environments where pilings degraded, and worker exposure during treatment and disposal prompted regulatory responses. Many countries eventually restricted or banned CCA for residential applications, though it remains widely used in industrial and agricultural contexts where its durability justifies careful management. This recognition that wartime shortcuts sometimes created long-term problems has driven modern research toward alternative preservation systems. Copper azole compounds, micronized copper technologies, and organic biocides that offer protection without heavy metal accumulation. Contemporary architecture and engineering still rely on principles established when survival demanded the impossible from wood. Long-span timber bridges, outdoor recreational structures in harsh environments, and sustainable building systems using engineered wood products all incorporate preservation strategies refined under the pressures of global conflict. The difference is modern understanding balances longevity with environmental stewardship and human health, recognizing that winning the battle against decay shouldn't create casualties in other domains. Lessons from the front. The future of timber longevity. These wartime innovations teach profound lessons about materials science under pressure. When failure carried catastrophic consequences, researchers and engineers abandoned incremental improvement for radical reimagining, and they didn't just make wood last longer, they fundamentally reconceived what wood could become through chemical intervention and physical treatment. This willingness to challenge assumptions, to view materials not as fixed entities but as platforms for transformation, remains relevant as contemporary challenges demand similar creativity. Current research into bio-based preservatives reflects this spirit, seeking compounds that protect wood through biological mechanisms rather than chemical toxicity, inspired by natural defense systems that have evolved over millions of years. Nanotechnology offers possibilities for molecular-level modification that wartime researchers could only dream of. Nanoparticles that penetrate wood structure to provide protection while maintaining the material's environmental benefits. Even genetic modification of timber species, developing trees whose wood naturally resists decay and insects, represents an extension of the same principle. That dire necessity justifies transforming wood itself rather than accepting its limitations. The enduring impact of conflict on material science demonstrates that even seemingly mundane challenges, like preventing wood rot, can yield breakthroughs that shape civilization. Those desperate engineers working to keep bridges standing and supply lines operating weren't just solving immediate problems. They were unlocking fundamental truths about how materials behave, how chemistry can transform physical properties, and how human ingenuity rises to match existential threats. The timber supporting your deck, the utility poles carrying electricity to your home, even the playground equipment in your local park, all exist because warfare demanded that wood transcend its natural limitations. That's the surprising truth about survival and innovation. Sometimes the most lasting peacetime benefits emerge from history's darkest conflicts. If you found these hidden connections between warfare and everyday materials fascinating, hit that like button and share this video with anyone who appreciates how history shapes the world around us. Subscribe to The Lost Tactician for more deep dives into the forgotten innovations, survival strategies, and material science breakthroughs that emerged when humanity faced its greatest challenges. because understanding how we survived the past is the first step toward thriving in the future. Until next time, stay tactical.